So today I will speak about some dynamic behavior for mathematical models involving infectious disease. More precisely, I will talk about COVID-19 model. Okay, so here we have just an introduction, short introduction about what does mean COVID-19 that I guess all of you know it already. So I will move directly to the mathematical aspects. Before we talk about COVID-19 model, I would like to present or introduce the general model for infectious disease, which represented by the unknown functions S, I, and R. S represented susceptible individuals, and I infected individuals, and R recovered individuals. And the other parameters are described in this table as you see. So this is the general form or the general model for infectious disease. So our idea, before we explain again the numerical parts for the evolution of solution to the basic infectious model, this one which represented by the following schemas. The parameters for these numerical parts collected from this reference that will be shown later. Now our idea is to introduce COVID-19 model with the help of a fractional calculus in discrete time. So we will add two unknown functions. Capital E means exposed or vaccinated individuals, and capital Q means quarantined, or sometimes we say isolated individuals. So we will combine this model with a fractional calculus, but in discrete cases. Okay, here we mean by delta alpha the delta variable order difference of our model in Caputo sense, where alpha of t takes values in the open interval 0, 1. Okay, and our parameters are described in this table. Some of them are assumed and others taken from World Health Organization. Okay, so we need to present a short introduction in from fractional calculus in discrete case. So our colleague in this morning presents some introduction about fractional calculus, but in continuous case. In our case, we will use a discrete case. So instead of fractional integral, we have here variable order sum, as you see, and instead of fractional derivative, we have here Caputo variable order difference. Okay, so let alpha of t positive and rename s plus 1 as sigma of s. So the delta variable order sum given with this form, such that this part is the discrete factorial functional which given with this expression. Okay, then for u defined on this set which appear here, okay, the delta Caputo variable order difference is given with this form, such that delta u with this expression is the forward difference operator. Okay, now in order to study our main results for this talk, we will present some auxiliary results needed or will be used later. The first one, Consider the following variable order discrete system with this form as you see. So what does mean the equilibrium point of this system? So the equilibrium point for this system are solution to this equation, f of x equals 0. And an equilibrium point is locally asymptotically stable if for all eigenvalues lambda I, as you see, of the Jacobian matrix, this one, evaluated with the following estimation. Otherwise, if this condition we have the opposite case, then the equilibrium point is unstable here. Okay. Other results concerning the criteria for the stability, which designate by these coefficients and A1 and A2 as you see. Other property here. So the characteristic equation in the n-order polynomial with this form, as you see, if all real parts of this equation root are negative, then the following inequalities will be satisfied. So all of them are positive. Now, suppose dk are real numbers and positive. So the Hurwitz matrix of previous equation is defined as square matrix of this size with this form. Okay, its determinant is given as follows with this form. Okay. So next, the previous polynomial has a real part of its root negative if and only if we have necessary and sufficient condition here. If the previous inequalities satisfied, means the determinant of the following parts, all of them are positive. Thus, according to this, the equilibrium point is stable if and only if the previous determinants are positive. So this is a necessary and sufficient condition for the stability. Now we are in position to state and prove the main results of this talk. First, we start to prove that our solution is not negative and bounded. So the solution of our considered model are non-negative for any initial values with this form, and feasible region of our model is defined with this set associated with this condition. So for the proof, I will try to skip quickly. Suppose our considered model with this form. So we will include the nil unknown functions for each equation to be reduced with this form. Here we set S equal 0 and here E equals 0 and so on. So after sample calculation, we will get that our solution is positive. Now we will show that our solution is bounded. So we just here apply the fractional order comparison theorem. Okay, as you see, we can conclude our result that our solutions are bounded. Now we study equilibrium points and basic reproduction number. So the basic reproduction number decides the stability result. So we discover the equilibria of our model. Let capital X with this form in terms of our unknown functions, and we set this equation, which is reduced form for our considered model. After that, we transfer our previous model to the following algebraic system, as you see. Okay. We use some algebraic calculations. We can find two solutions of our system. We have the first one called disease free equilibrium point denoted by P0. This is the first one in terms of S0 and R0. The others, of course, null. And the second one called endemic equilibrium point denoted as P star in terms of this new unknown functions, such that here S0 and R0 are given with the following expressions. Okay. Now we identify the basic reproduction number of our considered model in order to analyze the stability property. So we will use the spectral radius of the next generation matrix. Okay, so we consider this new vector, capital Y, in terms of exposed, infected, and quarantined individuals with this form. After that, we construct this new equation, this new one, in terms of capital F and capital V. We use the Jacobi matrix of the above at disease-free state P0 as you see. It is easy to get the following matrices. Hence, the spectral radius is defined by R0 will take this form. So we will estimate this form later to see the nature of stability. So the first result of stability here. So our considered model has a unique disease endemic, the first one, endemic equilibrium point P0, if and only if we have necessary and sufficient condition that this part greater strictly than 1. Okay. So for the proof, just some, I don't know if time will enough or not. So we consider P star with its form such that all terms are defined as you see, the same with its coefficients. So it is easy to get this last equation from the above statements. After that, we define this function g of x. It's the same, this one, from this part. So we move this part to the first member. So we rename it as g of x, which of course equals to 0 in this interval. After this calculation and having in mind the form of the basic reproduction number that given with this form, and the fact that g of x is continuously differentiable in this interval, we can have our result. Now we study the existence and uniqueness of solutions of our considered model. So first of all, we rename this part, the right-hand sides of our considered model, as new kernels from H1 till H5 in order to simplify the calculus. Okay, the first result, we prove that our kernels satisfy Lipschitz conditions. So we apply the sum, the delta sum on both sides of our considered model using the fractional calculus property. It is easy to get the following equivalent equations as you see, taking into account that this kernel is renamed as H1 and this H2 and so on. Okay, so it is easy to check that each kernel satisfies all Lipschitz condition by make the norm of this difference and estimated it provided this sufficient condition is satisfied with this Lipschitz constant. This is for the first equation, and we continue with the other equations. Okay. Now we use the following recursive formula with this form. So Sn here in terms of Sn minus 1, and we continue with all equations, and we use these initial conditions. After that, we take the expressions to above 1 for difference of successive terms. So we rename this part with this form, which given in terms of these sums, having in mind that we have the Lipschitz condition for these kernels. Here, Sn till Rn are given with the following finite summation, as you see. Okay, so we consider these new differences with this name. After that, we estimate the norm of each one with the right-hand side. Okay, so now we show that the existence of solution based on the previous analysis, provided that this sufficient condition is satisfied. So for the existence, we use the fact that our solutions are bounded and our kernels satisfy Lipschitz conditions. It is easy to get these estimations. We apply appropriately the limit as n tends to 0. It is easy to get these results, which mean we have the existence result of solutions. Now we prove the uniqueness property of solutions. So we will use the traditional way. Assume that our model has a second solution with this form, S2 till R2. After that, we make their differences, and this vector renamed as P is the Lipschitz constant. Then we use these differences as appear. We try to estimate their norms by using the Lipschitz condition on these parts. Okay. It is easy to get these new estimations. Okay. After that, we can check that these parts are negative according to the previous analysis, which mean we have the uniqueness of a solution. Okay. Now we have these figures shows the behavior of susceptible and removed, or we say recovered population for different values of the variable order alpha. Here we taken the usual derivative when alpha equals 1, and the other for different values of alpha. Here we can see that the fractional derivative gives better modeling for the system than the usual derivative. Okay, and now we study the stability of equilibrium points. Now we mean by the local asymptotic stability of equilibrium points. So The disease-free equilibrium P0 with this form, as we said previously, of our considered model is locally asymptotically stable if this basic reproduction number are 0 less than 1 and is unstable if R0 more than 1. So we use the Jacobian matrix of our considered model, and which estimated at P0 given with this matrix, with this form. After that, we use the characteristic polynomial capital G, which is represented by this form, where capital L of lambda is also given with this form. We try to estimate the coefficients A1 and A2 to understand the nature of stability. So we will have two cases. The first one, if R0 less than 1, we will have the locally asymptotic stability. Otherwise, we will have no stability. The next result is about the second case of the endemic equilibrium P star, which will be for opposite cases than above 1. So is locally asymptotically stable if now R0 more than 1. We use again the Jacobian matrix of our considered problem at P star, which is given with this form. All coefficients are detailed as appear. Okay, then we use the characteristic equation with this form in terms of zeta 1 till zeta 5 that given with the following forms. All of them are positive. And it is easy to check that all these determinants are positive, for which the equilibrium P star is locally asymptotically stable here. Okay, and here we have the behavior of exposed and infected population for different values of alpha. Here we have the usual case when alpha equals 1, and then we have different values for alpha. Okay, the same with the isolated population. Okay, and now we present some optimal control analysis. So the system, our considered system, will be modified as follows in terms of control function U, as you see. So the corresponding discrete optimal control problem with variable order in Caputo sense is considered with this problem, where the functional capital G is defined with this summation. Okay, and the control space omega is defined with this space, where here the coefficients C1, C2 till C4 represent the positive weight constant of exposed, infected, quarantined, and control variables. Okay, so let here U star denotes the optimal control variable of our considered control problem, and let S star till R star represent the optimal state solution. Then there exist adjoint variables K A satisfying the following equations associated with this sufficient condition. In addition, the optimal control U star is given with this form, the minimum of maximum as you see. Okay. So here we can determine the discrete optimal control U star as follows. We apply the discrete version of Pontryagin maximum principle to the discrete Hamiltonian function capital M, which given with this form, and we use the following formulations from control theory. After that, we can arrive at the new system in terms of K1 till K5 as you see. The control equation, this one satisfied. And we have also the control, the optimal condition, this one. And the control function U takes this form. Also, we have the optimal control U star given with this discrete form. And which can be reduced to this one. Okay, so here we have some numerical treatments. Here we have susceptible group with control and without control for different values of alpha. And the same here, we have recovered group with control and without control for different values of alpha. The same here for exposed individuals. We have exposed group with control and without control for different values of alpha. And here also for infected group for different values of alpha. Okay. Okay. And here for isolated group. Okay. Since the time is almost okay, so we have collected our parameter values from World Health Organization to investigate our improved system related to COVID-19 model. This is the main references for this talk. Thank you very much.